Hello and welcome to the EMC Live webinar, EMC Back to Basics. My name is Belinda Stachikevich and I'm the editor of Interference Technology, the creator of EMC Live. EMC Live is a brand new online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Matthew Carter, Product Support Engineer at Keysight Technologies. Matthew Carter is a support engineer working in the Microwave and Communication Division. He received a BS in Electrical Engineering from Portland State University, and he's currently focused on electromagnetic compatibility and vector signal analysis. This webinar is sponsored by Keysight Technologies. Keysight is the world's leading electronic measurement company, transforming today's measurement experience through innovation in wireless, modular, and software solutions. With its HP and Agilent legacy, Keysight delivers solutions in wireless communication, aerospace and defense, and semiconductor markets with world-class platforms, software, and consistent measurement science. The company's 9,500 employees serve customers in more than 100 countries. This webinar is one of many. To check out our others, visit emclive2014.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar today will be interactive. You'll be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We'll present the topic for 35 minutes, followed by a 10-minute question and answer session. Now Matthew will begin the presentation.
Good morning, good afternoon, and welcome to EMC Back to Basics. My name is Matthew Carter, and I'm joining you all from Santa Rosa, California. The agenda for today is we'll spend a few minutes looking at an overview of EMC, and we'll spend the bulk of our time today talking about emissions. We'll look at Keysight's latest EMI receiver. We'll look at a block diagram of that. And then we'll look at some measurement fundamentals and the basics to making an emissions measurement. And then finally, we'll wrap up with some other equipment considerations and some time for Q&A. So sources of electromagnetic interference. First off, we have natural sources from the weather, lightning, and sunspots. But the majority of EMI comes from man-made sources. We have products that unintentionally radiate, things like power lines, appliances, hair dryers. So these are all electrical products, but they have emissions coming off of them unintentionally. And the other category is devices that do intentionally radiate. We want them to transmit a signal, so things like computers with wireless LAN cards, cell phones, radars, etc. But the whole idea of EMC testing is that we want all these devices to be able to be in the same environment and to be able to operate without interfering with each other. Looking at EMC as a whole, you can look at it as a type of measurements out there. And we have, in general, emissions and immunity testing. We'll take a look at that in just a second. But you also have the application. Both of these measurements are applicable to commercial and mill testing. So emissions, what is emissions? So emissions are the signals that are essentially propagated off of a device. Radiated emissions are going to be the signals that spread through the air, can be picked up with antennas. And then conducted emissions are going to be the signals that propagate off cables. And most of the time, those cables are power lines that are connected to the mains. The issue here is that, for any EMI propagating off of the cable, there's other devices that are connected to the mains and potentially causing interference problems. The equipment needed for emissions testing is going to vary. At the heart of the measurement is going to be some sort of frequency selective device. In most cases, that's going to be an EMI receiver, but depending on the standard, spectrum analyzers can be allowed as well. In the case of radiated emissions, we're going to have an antenna and probably some sort of preamp connected to our receiver picking up the emission. On the conducted side, we need some sort of transducer to couple that interference from the device into our frequency measuring device, into our receiver. But on top of that, we also need another port to be able to power our device under test. And so in many cases, a LISN is the device being used, and we'll look at that later in the presentation. Let's pause for just a second, and I want to talk about compliance and pre-compliance measurements and how they relate to emissions. Maybe you've heard that term full compliance testing. Full compliance refers to the regulatory testing, essentially the final pass-fail measurement that's going to allow you to sell your product. It requires very specific equipment and test sites. They need to comply with the specific standard that you're testing to. Mill standards as well as commercial standards call out very specific requirements. But ultimately, full compliance measurements are very expensive and very time-consuming. So really, this full compliance test is something you only want to have to do once during the process. And what you can do to increase your chances of passing the first time is to do what's called a pre-compliance test. And essentially, this is an unofficial estimate that's done prior to your full compliance test. And really, this shouldn't just be a one-time deal. It should be an ongoing process throughout the design cycle. If you were to wait till the very end and you have issues, things tend to be very expensive to fix. Typically, pre-compliance measurements are done with a spectrum analyzer on location. Spectrum analyzers tend to be less expensive than EMI receivers, so that's why they're used. And then on location, so this could be a conference room or a parking lot. These are generally more available than multi-million-dollar EMI chambers. Okay, so continuing on, we were just talking about emissions. The other side of EMC testing is called susceptibility. Susceptibility is really the opposite of emissions. This is where we're actually injecting a signal, bombarding our device under test with a very strong electromagnetic field. Okay, radiated susceptibility, we'd be using some sort of antenna coupled to a power amplifier to bombard our device. And then conducted susceptibility, we're actually injecting a signal into the cable, maybe the power cable, and then seeing how this device reacts. Ideally, this device wouldn't react, but in some cases it will, and we need a way to monitor that. Okay, so you can see that there's no longer an EMI receiver or spectrum analyzer. That has been replaced with a signal generator, power amplifier. Signal generator could generate a CW signal, or in some cases we need some modulation, and that could be amplitude modulated signal to bombard the device with. On the conducted side, maybe you're going to use a LISN or some other device like similar to inject that signal. Now, if you look in the bottom left-hand corner, I have listed an oscilloscope for EUT monitoring. What is EUT monitoring? Well, when our device is in that strong field, we want to see how it reacts. Take, for example, an immunity test on a car, on a vehicle. We may connect the lights, or in addition to the braking mechanism, hook that up to channel 1 and channel 2. If the brakes were to release or the lights were to come on, that could indicate a failure. And using the oscilloscope, we can set triggers, so we don't necessarily have to be in the room to capture that result, capture that failure. Okay, so that concludes a brief overview of EMC. For the rest of the presentation, we're going to spend our time looking at emissions. And to start off with, we're going to look at Keysight's latest EMI receiver, the MXC, and we're going to walk through the block diagram here and understand the key steps, and how those are going to relate to an EMI measurement. So you can see the Keysight's EMI receiver in the upper right-hand corner. You notice that there's two inputs. This second input has a transient limiter, And transient limiter is very important for conducted measurements. Conducted measurements, you're going to have a listen or similar device connected to the front end. If you disconnect the receiver and the limiter in the wrong order, you can actually send a spike into the front end of the receiver and damaging it. So transient limiter provides protection during conducted measurements. What you'll find next after the transient limiter is an attenuator. The attenuator allows us to adjust the signal power going to the first mixer. This allows us to optimize our dynamic range, but also EMI signals can tend to be very strong, very impulsive. And if we get an RF overload, if all of a sudden our mixer has gone into gain compression, that can cause the EMI signals, the amplitude, to appear lower than they actually are. And that could potentially cause a device to fail, but actually it would pass. And so we don't want bad devices to slip through our test. Now, if you look to the right, you'll see that there's a preamp listed. Preamps increase the sensitivity of the receiver, and so it's very useful for standards that have very low limits defined. And one that comes to mind is MIL standard 461. So for MIL testing, some of those limits have very low limits. Both the attenuator and the preamp, we actually compensate for those either losses or gains on the other side of the mixer, so that no matter what the settings are, we're going to measure an accurate signal level on the screen. You know, imagine if you're adjusting your attenuator, and as you do that, the signal on the screen is decreasing. Well, that's not okay. We want to accurately measure it, so we have some compensation. So moving right along, after the preamp, or actually between the preamp and the attenuator, we have what's called an RF preselector. And it's essentially a bank of filters. We actually have 18 filters in the front end. Most of them are bandpass. And the function of the preselector is to reduce the amount of broadband energy going to the first mixer. You know, we could use the input attenuation, but what we'll find out later is that as we increase the attenuation, our instrument actually becomes less sensitive. Okay, and sensitivity is one of the key specs for EMI measurements. So by using this bank of filters, we're still reducing the amount of energy going to the mixer, but still having great sensitivity. You can see this illustrated in the upper right-hand corner. This blue line here is meant to illustrate one of the preselector filters. You can see that it's for, you know, at a certain point during the sweep, it's filtering out the broadband signals and only measuring narrowband signals, so limiting the amount of energy going to the first mixer. So after we've gone through the attenuator, the preselector filters, and the preamp, our signal is going to get down converted via the mixer, and it's going to get down converted to what we call the IF, or the intermediate frequency. And at the IF, it's actually going to go into what we call digital IF, where we're digitizing the signal with an ADC, and then we're processing it with the digital signal processor. So what happens in the DSP? Well, that's where the resolution bandwidth filters and the detectors get implemented, and we're going to go into more detail in just a few minutes. And then lastly, the log amp is also implemented there, and the log amp gives our display in terms of dBs or decibels. Now, when spectrum analyzers were first invented, they had an analog IF in that all the components were analog or mostly analog. And by going to digital, really the key improvement was improving amplitude accuracy. With digital, there's no longer any switching uncertainties or amplitude uncertainties related to the display, so there's a significant improvement there. Also, a secondary benefit is that it makes the receiver more general purpose. And what do I mean by that? Well, going digital, we have FPGAs in there. It allows us to reprogram the instrument very easy. Imagine, now you can just download new firmware instead of, a number of years ago having to perhaps send your instrument in and do a board change, requiring a hardware change. Okay. So with that concludes the block diagram. However, I left out an important piece, and that is, what are the different scan types? How do we collect this frequency information? Historically, the step scan was used. And the step scan is essentially the LO tuning to a frequency and then waiting there while we dwell and measure that frequency point, and then retuning to a new frequency. And we did that across the span. Now, it turns out that this is actually the slowest method, and that's because we're having to retune the LO for each step. A slightly faster way to do it is what's called a swept scan, and this is similar to what spectrum analyzers do. The LO sweeps in frequency, okay, so it's connected to the mixer, which causes the input spectrum to sweep through our IF filter. Now it's slightly faster because we're only retuning the LO once per sweep instead of once per frequency point. But overall, due to the long dwell times, it's still very, very slow. Then, lastly, what was introduced in 2010 is called time domain scan, and it's essentially a very fast, highly overlapped FFT. And it's allowed for pre-compliance measurements as well as full compliance measurements. Now, to illustrate the time savings here, I have a slide. On the left is traditionally how measurements have been made, swept or stepped. You can see the outline of the resolution bandwidth filter. For each frequency point, we're dwelling on an order of milliseconds, but for several thousand points, that time starts to add up very, very quickly. So think of this as serial processing, one point at a time. Now, where's the benefit with time domain scan? Well, with time domain scan, we're taking a chunk of spectrum. Could be up to 25 megahertz depending on the frequency. Okay, and we only have to dwell once for that whole entire chunk of bandwidth. But what we're getting is multiple resolution bandwidths for a single dwell time. Okay, so that's where the time savings is. And really, this method, time domain scan, is like parallel processing. The swept and step scan is like serial processing. That's a good way to remember it. Okay, so with that, that concludes the block diagram of the receiver. Let's go ahead and move on to measurement fundamentals, and then we'll look at the basic steps to making an emissions measurement. Okay. So this section, we're going to focus on sensitivity, and we're going to look at how sensitivity is a function of the attenuation, the preamp, and also the resolution bandwidth. Okay. So sensitivity, this is probably the key spec or one of the key specs for EMI measurements. We want our equipment to be very sensitive. Okay. So sensitivity is the smallest signal that can be measured. And if you were to look in a data sheet or specifications guide, you'd probably see sensitivity specified as DANL. Now what's DANL? Well, DANL is short for the displayed average noise level. And you can see that it has units of dBm per hertz. dBm is a power, and hertz is a bandwidth. Okay, so the noise level is a function of the bandwidth, function of the resolution bandwidth filter. Okay, so what's the relationship here? Well, if we decrease the bandwidth of the IF filter, the resolution bandwidth filter, we decrease our noise. So every factor of 10 that we decrease the bandwidth, you see a 10 dB improvement or 10 dB lower noise floor. Okay, so that's one way to improve the noise floor. However, for compliance measurements, the standards call out very specific resolution bandwidth. So commercial, we have the CISPR reference bandwidth, and for military, Mil Standard 461, they call out 6 dB RBWs. So for pre-compliance measurements, it may be okay if you need to improve your noise floor, but you need to use very specific RBWs for compliance measurements. Now, one of the other consequences of changing the resolution bandwidth filter is frequency resolution. Now, imagine, if you will, you have an input spectrum of two tones, one higher, one lower. You can see that on the top. And as you decrease your IF bandwidth, RBW, if your two tones fit within that bandwidth, all that power is going to get averaged together, and it's only going to look like one signal. So you can see that in Figure A. But as you start to decrease it more and more, and you get to a point where only one of those tones fits within the RBW, resolution bandwidth, all of a sudden you can tell that there's two signals. Okay, so see, that's in Figure C. So smaller resolution bandwidth, better frequency resolution, better noise floor, but the trade-off is slower sweep time. Okay, so sensitivity, it's a function of the bandwidth, the IF filter, but it's also a function of the attenuator. You can see here two diagrams. And as we change the attenuation from 10 dB to 20 dB, the signal level is not changing. And remember back, I said that's because we actually compensate for that on the other side of the mixer. Okay, so that's important. Signal level does not change as a function of the settings. But what is happening is that as the signal goes through the attenuator, our signal-to-noise ratio is decreasing. But since signal level is constant, that means the only thing that can change is the noise floor. And the noise floor is going to increase as the attenuation increases. And that relationship is, for every 10 dB of attenuation that you add, you're going to see a 10 dB increase in the noise floor. So the takeaway here is, to get the best possible sensitivity, is you want to use as little attenuation as possible. You can also use the preamp kind of in opposite fashion. The preamp is going to improve your signal-to-noise ratio. Since the signal level is going to be staying constant, that forces the noise floor down. Okay, so in summary, use as narrow resolution bandwidth as you can, but remember, for compliance measurements, they call out very specific resolution bandwidths. Probably a better choice is to use as little input attenuation as possible and use either the internal preamp or an external preamp. Okay, so let's look next at detectors. What are detectors? Well, before we talk about what a detector is, let's look to history. And before we had digital EMI receivers, we had analog. Imagine analog IF, and with analog spectrum analyzers or receivers, what was displayed on the screen was a continuous indication of what was being measured. And one of the issues that we had was that for very slow sweep times, a dot would appear on the screen and it would slowly trace across the screen. And we tried to get creative. We had persistence displays, and you would have to adjust the knobs for each, depending on the sweep time. So that was kind of a fix, but ultimately by going digital, by sampling the signal and having trace points, trace memory, we were able to get around this issue. Now, what happens with digital is that all of a sudden you have, a certain number of pixels on the screen, you have trace points, and you have to figure out, what is that trace point going to be? Each trace point represents, a certain frequency span, and it also had to be measured over a certain time interval. So, well, how do we calculate the frequency span? How do we calculate that time interval? Well, fortunately, I have the equations listed on the screen. That bucket, I'm using that word bucket as also as a trace point, so frequency bucket width and time bucket width. So you can see, if plugging in the span in our example here, 100 megahertz divided by 1,000 trace points comes out to 100 kilohertz. And then if you do the math for the time bucket width, 10 millisecond sweep time divided by 1,000 trace points is 0.01 milliseconds. So each trace point is 100 kilohertz wide, measured at 0.01 milliseconds. Okay, so now let's zoom in on a single trace bucket, and that's what we're looking at in the bottom right-hand screen. So one bucket, and if you look at the X scale, that represents the 0.01 milliseconds. Well, while we were measuring over that 0.01 milliseconds, we were measuring multiple values. We can see a peak, we can see a trough. How do we know which point to pick from this bucket and display on the screen? Well, that's where detectors come in handy. Detectors ultimately dictate what is going to be displayed on the screen. If we were to select the peak detector, we would select the peak in the bucket, and that would be the value displayed on the screen in one of our trace points. The average detector would average all these values together and then take that single value and use that as the trace point. And then the quasi-peak detector. Quasi-peak was developed to characterize the annoyance of the signal. Now imagine listening to a radio and you hear some popping. Pop, pop, pop. That's annoying, but you can still listen to your favorite radio station. You can still get information from that. But imagine you were listening and you heard 60 pops a second. Well, that's no longer usable. And quasi-peak was invented to characterize that annoyance factor. Some of the characteristics of quasi-peak is that it has a very fast charge time, but a slow discharge time. And the output is not only a function of the amplitude of the signal, but the pulse repetition rate. And that's just a fancy term for saying, how often is that signal occurring? Is it annoying or is it not so annoying? And then lastly, the peak, average, quasi-peak detectors are what are commonly used for commercial measurements. The peak detector is the only detector accepted for mil standards. Okay. So then lastly, measurement time. I indicated that for each bucket there was a certain time interval that we had to measure over. Time interval, measurement time, these mean the same thing. I'm going to be using those terms interchangeably. Now there's a variety of reasons, wanting to reduce test time. Some reasons are technical in that the device that you're measuring requires a short measurement time, such as a motor starter. Motor starters you can't run for hours and hours. The typical EMI test, you're going to burn it out. And there are other similar devices. Other reasons, maybe business reasons, is you're wanting to test more devices or have a shorter turnaround time. But ultimately, the standards bodies define speed limits. You can only go as fast as the standard calls out. Okay, and these are called minimum measurement times or dwell times, and they're specified for both commercial, so CISPR, as well as mil standards. And the reason they do this is that they want to ensure that you're accurately measuring your signal. It could be an impulsive signal. Your signal could be varying with amplitude over time, and so you need to ensure that you've measured that signal for long enough to capture the peak of that signal. Okay. So to give you an indication of some of these measurement times, for commercial measurements, you can see in blue the scan times for the peak and also the quasi-peak versus frequency, and then the same for mil standard in the orange. Okay. So with that, let's look now to making an emissions measurement. This methodology is actually recommended by CISPR. You can find it in CISPR 16.2-3. Now for mil measurements, it's much more simplified. Essentially it's scan with the peak detector and you're done. There's no pre-scan data reduction and maximization. So go ahead and keep that in mind as we look through these steps. So step one, according to CISPR, is to do a pre-scan. And the pre-scan is basically taking a preview of the spectrum using the peak detector. Peak detector is going to give you the fastest sweep time compared to quasi-peak and average, and that's because we're just picking the peak value out of that bin and we're moving on. Okay, so We can see a preview of the spectrum here. We have our limit line turned on in yellow, and any signals that are above the limit turn red. Okay, and we can also see our trace fail. We essentially want to go as fast, well, not quite as fast as possible, but to quickly get a preview. And then we're going to want to do data reduction. We're going to grab those signals in red, we're going to put them into our signal list, and we're essentially getting rid of everything else, getting rid of all the other signals that aren't failing. We don't care about those signals. We're just setting ourselves up to do a final measurement on only the signals that are failing. Step 3, signal maximization. What can happen is when your receiver does this all automatically, we'll sweep and then grab those signals, put them in the signal list automatically. It may not always grab the center frequency of that signal. In addition, if your signal is varying with time, you're probably going to have to measure longer than that minimum measurement time defined by the standards. Okay, and you need to capture that maximum emission. Well, how do we do that? Well, there's a variety of tools out there. One that I really like that we have in the EMC is called Monitor Spectrum, and it's a simultaneous display of the spectrum. We're doing an FFT on the data. You can see that on the left. And then we also have the meters, and the meters give us an insight into the time domain. It allows us to monitor a certain frequency and see how that behaves with time. So we can capture the instantaneous value, but also the max hold value. What was the max hold value over 15 seconds, a couple minutes, or a couple hours, whatever it takes to get that maximum amplitude. On the right, we also have a linkage between the spectrum analyzer mode and the receiver mode, and that provides similar functionality. But despite whatever tool we use, once we've captured that maximum emission, captured the center frequency, we want to do final measurement. Final measurement is for those signals that are still failing the limit. We're going to measure them with the quasi-peak or average detector. Really depends on which standard you're testing to. And depending on the characteristics of the signal, it could actually be passing with either one of these detectors. It's entirely possible to fail with the peak detector, but then to pass with quasi-peak or average. Now hopefully our device would be passing at this point. If not, it's time to go back and start troubleshooting, figuring out where that issue is happening. Either way, pass or fail, you're going to want to generate a report. If your device is passing, you're going to use that data to submit to the regulatory authorities. And if it's failing, you want to be able to capture the spectrum, compare that to your second test after you've made fixes to your device. Did it help? Did it make it worse? But it provides data points for that. So with that, for the most part, we've been focusing on emissions, but there's a lot of other equipment that is required to do emissions testing, and so I'd like to just spend a few minutes talking about that. First off is automation software. So this is a growing trend. Lots of people in the industry use automation software. First off, it's used for automatic data collection from the receiver, in addition to controlling external devices such as turntables to automatically rotate the device, operate any antenna towers. By having a computer do it, it's going to reduce the test time, especially since these setups can be very complicated. If you're testing multiple standards, everything varies. But probably most important is getting measurement repeatability. By having a computer do it, the test is subject to human error. Computers are able to do it much more accurately and repeatable. The software typically talks to the receiver over a LAN or a GPIB cable. I've also seen it done with fiber optics. And the reason people are using fiber optic cable is just to reduce the emissions within the chamber or whatever their test site is. And then the language that the software and the receiver use to talk to each other is what's called SCPI. And SCPI stands for Standard Commands for Programmable Instruments. Okay. Now, next, transducers. So transducers are what allow the receiver or the frequency selective device to measure the outside world. And we have transducers for conducted measurements as well as radiated. So let's take a look at conducted. Earlier I mentioned this device called a LISN, and LISN is short for Line Impedance Stabilization Network. And really, the purpose of a LISN is to connect it to the mains, so we need to be able to power our device. But it also isolates any noise that our device is producing from the power mains, so it doesn't interfere with anything else. But also, if there's any noise on the power mains, we want to isolate that from our device under test. And then finally, it allows us to couple our receiver and measure the emissions that are coming off the device under test. Next, transducers for radiated measurements. We have two choices. We have antennas and probes. Probes are typically just used for pre-compliance testing. And that's one of the reasons is that they don't have sufficient sensitivity to measure at 3 meters, 10 meters, whatever the required distance is. You have to be far enough away to be in the far field to make these measurements. When selecting a probe, first off, you want to make sure it has sufficient frequency range. Second is you need to consider the spatial resolution. So probes come in all different shapes and sizes, some big, some small. The smaller the probe, the better spatial resolution you'll have. It can enable you to measure two very small ICs that are, very close together. The trade-off there, though, is that as you have a smaller probe, your sensitivity decreases. Okay, so there's got to be a balance between spatial resolution and sensitivity. And then lastly, we've just talked about using probes for measurements, but you can also use them to generate a local field. Imagine you're wanting to test your processor or your little IC, hook up a signal generator, generate a local field, see how your device under test reacts, and you're able to test different components that way. Now for antennas, I don't have time to talk about each one of these, but some typical antennas used for EMC measurements. Now, really the glue between the antenna and the receiver is what's called antenna factors. An antenna factor is simply the ratio of the field, electromagnetic field, to the voltage coming out of the antenna. So voltage is what the receiver can measure, and the antenna factor tells us what is that ratio of the voltage to the field strength. It is a function of frequency, and here I've listed an antenna factor for a typical biconical antenna. Okay, so you can see how that varies. Good way to know if antenna factor has been turned on in your receiver is that the noise floor is going to look kind of funny. Here you can see it looks kind of wavy, so that's a good indication that it's been turned on. Typically, a noise floor of a EMI receiver is going to slowly drift upwards from left to right. And then lastly, a few words on test environments. So obviously, we need somewhere to make our EMI test. First one, and probably the most expensive, is an anechoic chamber. Anechoic chambers are, first off, shielded, so we're preventing signals from the outside from getting in. But then they have anechoic material on the walls and sometimes on the floor, and that's to prevent energy from reflecting, from setting up standing waves that can interfere with the measurement. We also have less expensive options, such as an OATS. OATS stands for Open Air Test Site. So these are going to be less expensive. They're outside, but the issue is that you need to have an environment that has low ambience. And that can be very hard to come by these days, considering, a lot of people have cell phones, and, really the spectrum is getting more and more crowded. Other options, less commonly used, are reverberation chambers. These are chambers that do not have any kind of anechoic material on the wall, no absorption material. And they'll actually use what's called a stirring tuner to actually get a uniform field. So they want the signals to bounce and to get standing waves, and then they create a uniform field. So with that, that concludes today's presentation, EMC Back to Basics. If you have any questions, go ahead and type them in the chat box. Be happy to answer any questions you may have.
Thanks so much, Matthew. We have 5 minutes left, so we are going to go for some questions that we received. We're going to go over to Eileen from Keysight, who is going to ask Matthew some questions. Eileen?
You might be on mute.
Eileen, you want to unmute yourself? Don't know if we're having a few technical difficulties, possibly. Let's just start with one until she comes back. Matthew, calibrate equipment is very important for EMI measurements. What kind of calibrations do you offer?
Good question. So we have a variety of calibrations. We have our standard factory cal that ensures the equipment meets specifications. Probably what most folks interested in an EMI receiver are going to want an accredited calibration, so 17025 accredited calibration, and that is what most EMI test labs, EMI test facilities want to ensure they have valid accreditation. And so, yeah, so accredited calibrations is probably what you're after, and that's what we offer.
Okay, great. What's a reference bandwidth?
So reference bandwidth, that's a term that CISPR uses. CISPR is essentially it's an international organization, and one of the documents that they've defined, CISPR 16, is all the requirements that a receiver needs to meet to be commercially compliant. And in that document, they call out specific reference bandwidth. It's essentially the same thing as a resolution bandwidth, and resolution bandwidth is the IF filter. Basically, we're down converting, and then the signals get filtered through that. But that's just the term that they use. But those terms are synonymous. So that when we looked back earlier, what was it, the 200 hertz, the 9 kilohertz, 120 kilohertz, 1 megahertz. These are all the reference bandwidths or resolution bandwidths that CISPR defines and requires.
Okay. Is there a way to plot my emissions measurement over time?
Sorry, you broke up there for a sec.
It's okay. The question was, is there a way to plot my emissions measurement over time?
Yes. So there's a variety of ways to do that. We have two spectrogram and the strip chart. Spectrogram, I've also heard it referred to as a waterfall display, so it displays the trace data over time, and different colors represent the different powers. The strip chart's a little bit different. There's different applications. Strip chart will display one signal over time, but then it allows you to see the response of different detectors, and you could display up to 3 detectors. So, for example, I could tune to, say I had a signal of interest at 100 megahertz, I could display the response of the peak, quasi-peak, and average detector all at the same time to get, an idea of how that signal varies over time. But ultimately, spectrogram and strip chart are the two tools to use to monitor signals over time in a spectrum analyzer or receiver.
Great. Thank you so much, Matthew. We've received a lot of questions. We really appreciate everybody's responses. We hope to get to them soon. We'll try to address them in the future. Matthew, thank you again for your time and expertise. Webinar attendees, if you have any more questions, we didn't answer here, please send us an email at info@emclive2014.com. A recording of this webinar will be available on our website. We'll also send a link to all participants shortly. Thank you for attending.